Hello and welcome everybody to one exciting course, Deterministic Operations Research. This is a really super area of research and decision making tools that has really only developed in the last 50 or 70 years. So let's get started. This week we're going to start off week one, chapter one is all we're going to do in the book. So please make sure you have that ready. Now, as a background, operations research we're going to find is an art and a science, right? It has a history of about 70 years now, and it is a way to drive business decisions that includes forecasting, modeling, inventory control, and etc. So, operations research is that activity that's carried out in an organization by testing through this scientific method a situation, a problem. We'll construct a model, we'll validate it, and we will make decisions based on it. So, frankly, it's a quantitative approach to decision making. As the book starts out, it says that the operations problems are no longer limited in space to the physical laws, right? So we're taking non-physical things like the supply chain, turning it into a mathematical model with its variables, and we're describing the relationships and features to help us make important decisions. That's what we call operations research. So, operations research is that approach, this mathematical model, scientific approach to decision making. We're going to talk about what that math model should look like and along the way. So, what we do, right, as professionals in operational research, or sometimes just called OR, right? We're looking for a rational way to make decisions, right? So we want to understand these complex situations and predict or improve them based on analysis. So we'll assess the variables, we'll assess the constraints, turn it into a mathematical model called linear programming, right? And so just to note, the British refer to it as operations research. Americans will use that too, but in America we also use the term management science. This is common, or sometimes you'll see it abbreviated OR/MS. It means the same thing, right? Sometimes you'll even hear it called industrial engineering or decision science. We're going to call it OR in this course, but just know that it can go by other names. Now, in addition, I'd like to note that there are two forms, deterministic and stochastic, right? We are focused in this course just on the deterministic approach. So, deterministic operations research is going to use fixed parameters to optimize a decision, to minimize or maximize some function. We are not going to go and discuss the stochastic models. This course, that would be for another time. But to further break them down to make it clear what we're working on, we are going to be working on, for example, linear programming, which will start this week. In the following weeks, we'll talk network optimization, including the nodes in a schedule, resource management, transportation models, etc. The stochastic models are going to be a little more in depth. We're not going to talk about queuing theory. I love game theory, but not part of this course. Just to differentiate in case you're using online resources to review other information. I just want you to be aware of that, okay? Now, OR has a history. I won't go into it too much, but frankly, it's about 70 years old. Really began in the late 30s, accelerated by World War II. So here are some highlights on what might be considered milestones in operational research development. You could Google any one of these to get a little more background on it. But frankly, World War II accelerated, or post-World War II accelerated this approach. There are basically some problem-solving steps along the way. Some say 4, 5, 7, right? What you want to do is identify the problem first, and then you want to collect data, right? But while you're doing that, you can determine a mathematical model, which is a way of determining the problem, right? So we define the problem, and then we create solutions using this mathematical model along the way. And then we're going to solve the math model by looking at decision variables that provide the minimum or maximum objective function that we're looking for along the way. And then we're going to make our real-world predictions or results. If you have the book available, they give a good description of these steps on pages 3 and 4 of the manual, right? These steps are not essential. I just wanted to guide you. You won't be tested on them. I'm going to give you steps here shortly that I want you to follow. These are just meant to give you an overall big picture on how we're going to solve problems using this approach. In fact, the next few slides are detailing this problem-solving process. So we'll start in the top left with the situation. Then we'll formulate a problem statement. We'll look at the models that might help us solve this. And the tools we're going to focus on are the deterministic tools for operations research. Then we're going to test that solution and continue to collect data. So this slide discusses part 1, the situation, right? It might be a current operation, or it might be a market shift, and we're wondering how much money we should invest in building certain products. Maybe it's customer complaints that's driving us to it. For example, and this is a real life situation happening for a friend of mine right now. Internal nurse staff is not happy with their schedule, and the hospital is using too many external resources and not allowing them to optimize patient care. So it's really being applied. That's the situation going on right now. Now we want to formulate the problem then, right? So we want to describe the system. This is going to help us form our mathematical problem, because notice we're defining our variables and the constraints or limits, and then of course the requirements, among other things. So in this case, I want to maximize the nurse's preference subject to the demand requirements is how I might solve that. Then I want to collect some data, right? Data preparation is absolutely crucial in this OR effort, right? And it's going to minimize our errors over the long term. So we're going to continue to test the data along the way and our model. And because some of these models will have 50 decision variables and 25 constraints. Holy mackerel, you can have, thousands of data elements. It can be quite extensive. So we'll continue to assess and validate. And so what we've done now is we want to construct a model. So we want to take, and we're going to just use OR, deterministic OR in this course. So we've taken the problem, translating it now into verbal and qualitative terms, right? And we're going to create this logical model, this mathematical model, which is going to demonstrate relationships between variables based on the constraints that are put on us in the system. And there's my nursing example there down below. Now, the advantages of modeling is that it generally means that it requires less time, it's less expensive, and we get a better decision right off the bat, so there's less risk involved. Now, So our focus now is on these mathematical models. So we want to get to know these terms. So for example, decision variables, these are our controllable points, right? They can be fixed or variable. We're going to largely work with fixed. Remember, we're going to seek in the objective function to maximize or minimize an item subject to the constraints. So we'll want to define the decision variables, we'll want to define the constraints, and we'll want to define what we're trying to maximize or minimize. That's the objective function. Sometimes we have stochastic, as I mentioned. We're not going to do that in this course. Otherwise, we are going to only pursue deterministic operations research, right, which are controllable parameters or inputs, right? These controllable decision variables, okay, to seek an optimal solution. So here's a simplified flow chart of what that looks like. I have these uncontrolled environment, and I want to have controllable decision variables or inputs, build my mathematical model, and predict my outputs. That is it in a nutshell. So for example, I might want to do a project that centers around scheduling. So a construction company wants to build 250 unit apartment complex, right? It's going to have lots of activities, wiring, plastering, etc., right? So what is the best schedule for the activities, and which activities should additional resources be purchased to enhance, right? So I might have this question. I might want you to suggest assumptions that could be made to simplify any scheduling model, right? Well, I might use then the deterministic approach by assuming a normal and expedite normal activities, right? There's no random wild variation, right? Assumptions about constants, right? Like weather in the time of year, or pay, or work hours, etc. Then I might ask, well, how can this management science approach be used to solve this, right? Well, through this modeling, I'm going to create this quantitative approach to minimize the completion time based on normal activity times, right, along the way. And so I might then say, well, what would be the uncontrollable inputs, right? So maybe there's expedited activity completion times. Maybe it's funds availability or precedence relationships. This is all just background. Don't worry about the details. Just get a feel through this conversation about OR. Now, then I might say, well, what would the decision variables be in my mathematical models? You know, what's the objective function? Well, the decision variables are those activities that I want to expedite, and how much and when. The objective function would be to minimize project completion times, and my constraints, whatever they are, I want to make sure they do not violate any activity precedence relationships along the way, right? So in this process, then, I want to solve the mathematical model. If you remember the picture that we had just a few slides back based on slide 12, right? So we have this model, and we want to consider the tools to create a solution, right? We want to create a mathematical model that optimizes our solution. It's either to minimize or maximize along the way. Okay, I am going to pause there. We'll come back to modeling the solution and do a quick example, and then we'll off to try some tests online.